Hey, good afternoon from lovely Florida. I'd like to welcome everybody to our webinar session today. I'm happy to introduce myself, Mark Hendricks with DEHN Lightning Protection here in the USA. I'm happy to introduce the rest of my colleagues. I have my organizer is Stephen Weber, who is our senior design engineer here in DEHN USA. We are happy to make some introductions. After we get through that, I'm going to go ahead and kill my cameras to help with the fidelity of the call. So again, welcome everybody. Thanks for your participation. So who we are, DEHN Lightning Protection. DEHN SE is a 110-year-old company out of Neumarkt, Germany. We really are the global leader in lightning protection systems, applications, pioneer in surge protection products, and in grounding and earthing products. Very active, chairing many of the technical committees in the global standards, participate with IEC, UL, NFPA. In addition, we participate heavily in the local standards from our other DEHN subsidiaries, my colleagues in South Africa and in other parts of Europe and China and India. We're all very active in the standards and working groups. And DEHN is happy to say that we actually wrote the Red Book on lightning protection methods. It's a college accredited book. It's got a ISBN number that we're very happy to make sure is available to our customers. So our session today, we have several key aspects of the fundamentals of lightning protection that we'd like to discuss. And we can show you that here. This is we're gonna talk a lot about the step leader attachment science. That's sort of the best understanding of lightning propagation that we can share. We want to talk a lot about the electric field and how that provokes step leaders that actually form lightning attachment. We'll talk a lot about the final attachment, return strokes, the amplitude ratings, things about the facts about lightning that we use mathematically to try to simulate and understand what nature is doing in many varieties. We talk about, charge, the propagation of charge. That really helps to understand what's provoking the electric field and what's occurring. And then we'll present the pillars of LPS, like that really that you really need all of the components in a lightning protection system to make it effective. Otherwise, you're compromising any one of these, for instance, can reintroduce the risk of lightning damage, fire. We have some closing comments and a few questions. This session is intended as sort of the introduction to the topic. We are also going to be conducting several more webinars on these topics, and these sessions are intended to be an hour long to provide Florida professional engineering credits for our attendees. The planned topics are listed here that help break down and walk through the material in a lot more detail, in real practical detail. So these sessions are set up to be accredited. You can see that we were planning sessions on Thursday, the same time slots, and we really look forward to having our audience attendees help participate in that and make that a success as well. And this is what we have planned. You'll be seeing a lot of this on social media and on our website to help bring the topic to life. Okay, well, formation of lightning discharge. This is really where we like to start, because it's as I mentioned, it's sort of the best understanding of what's happening. And there's really great slow motion video. There's really great science from leading academic and industry experts, and it shows that lightning is the motion of charge releasing from the atmosphere in either cloud to cloud, cloud to space, cloud to ground, ground to cloud. It's lots of who's who in the zoo, but it's charge builds up to a point where the electric field is so strong it rips through air and releases to ground. And that's what we humans find of interest, is releasing to Earth, and that is a source of fire and damage and risk. The charge builds up to such a huge extent that it's able to propagate through miles of atmosphere. So many of us have had the question, wouldn't it be great to capture some of that energy and have free electric energy? Yes, if you can build a system that is the equivalent isolation and dielectric withstand of 10 miles or so many miles of atmosphere, you could theoretically grab that charge usefully and do something with some effective work, theoretically. But what we are able to do with our understanding of lightning today is to safely divert that charge into the Earth to avoid damage. So we're trying to prevent, a fire, and just to keep our structures, from being destroyed by lightning. So collecting lightning would be an interesting theoretical topic. So the propagation of lightning, it is known to jump through the air in bursts and step leaders. And I really like this slide where we pause, because this is that depiction of charge provoking an electric field, and everything within the electric field will respond relative to that dielectric strength of the air around it and that distance to the charge. So what's really interesting about this slide is that it's showing tendrils, step leaders, trying to form and reach what would be the main body of the charge. And at some point, the dielectric field withstand bursts through, and you get the final step leader attachment. And then you get what's considered the attachment, and then the return strokes. And there's a lot of great science that talks about all that impulse and the varieties of that as well. But I really like that slide that showed all the smaller step leaders being provoked. And in the electric field, you would see that at a certain distance, that step leader distance, all bets are off. Who is actually going to make that attachment? And even if you don't get the main attachment, you're still getting plenty of lightning juice into, say, the side of your TV antenna. There's a really great photograph from, I first saw this in National Geographic, but it's titled as "Sycamore Tree: a convincing argument not to stand under trees during a lightning storm." And you see a real lot of really great science in this photo. It's actually considered one of the best illustrations, an actual photograph of the event. And in fact, this is the cover of a very respected book from Martin and Rakoff on the topic. And what you're seeing is in that bursting final attachment, you've got all the science of the plasma channel being formed, but you still have many step leaders unresolved that are still trying to reach out. And what's really great are the small leaders that did not attach from, in this case, it's part of the tree and probably the background, that some trees may be back behind. And also you'll see a bit that's trying to attach to the little TV antenna to the house. There's a lot going on, and this is just the terrestrial side. There's stuff going on in the cloud to cloud. There's all sorts of tremendous phenomena that we're studying, that the science is studying of sprites and all the little things that are going up into space above some of the more powerful thunderstorms. But even this little bit of lightning that struck that antenna is able to blow out the electronics of the house here. And in the report, the subsequent article that actually accompanies this photo from National Geographic, it described that the TV was still blown apart inside this house. It's a good old UHF VHF antenna up on the top of this country house. But what's really great about this is that you're really seeing a great depiction of these step leaders here, that some that didn't form to the ground, but the other ones reaching up. And so in your mind, you can pick a point, say, where there's a charge. Before this final attachment, the charge was moving through the air, and in those nanosecond, microsecond long stationary pulses while it's jumping, it's forming an immense electric field. And for those moments, it provoked these step leaders to try to grab the larger charge to form the step leader attachment, and the tree won or lost, probably becoming a great source of firewood for the farmhouse here, because you can picture a radius that step leader will attach. And that is the basis of a lot of the modeling of how lightning will attach to a structure. So we use that step leader, that striking distance of that final attachment, as a planning method of where to locate lightning rods. The intent of the lightning rod is not to scare away lightning, it's not to draw lightning, it's to give what's going to attach a preferred path to ground. And that's really what we're trying to do, is put a lightning rod on that structure so that if it's going to attach anyways, you give it a path safely using the pillars of lightning, what we talked about, the air terminal, down conductor, earthing system. But we're building it a better path through the structure, around the structure. So Ben Franklin, on or around 1752, he figured out the lightning rod and stopped fires. So he patented it and then immediately released it into public domain and promoted it as a method to prevent lightning damage to structures. And it works. And what we didn't know a lot about in the battle days, we've come to better understanding of each of the methods, and basically what he did was put an air terminal, a down conductor, and a spike into the soil. Well, we have better science and we understand more about that. And so that's helped drive our standards over to the point that we're at now with the understanding of lightning. So lightning characteristics. So one of the great things about nature is that it only obeys mathematical principles, and lightning is no different. Everything we know about lightning comes from you can see it and understand it. Now, it's very hard to describe it mathematically for each event, but we can measure and see what's going on, and we can analyze all the magnetic and RF fields that are being generated. So the parameters of interest that we use in the course of specifying and designing and trying to create a safe environment: charge, which is the motion of charge through the atmosphere, and charge is what helps you understand what the amount of current and the time duration is going to be. So charge is a key factor. Mathematically, you can see it links to current. Current is the peak amount of current created in that plasma channel. Lightning is a DC event, so it's, even though it looks like a very rapid pulse, the lightning plasma channel is only conducting current in one direction. When the lightning energy is dissipated, it doesn't rebound back up, so to speak. It's only pulsing energy one way. So think of it like a big, fancy, complicated DC event, one direction. But still, that current has a peak value, and that is another measure of that's mathematically derived, and we can calculate it. The steepness, the DIDT, how fast and the rise and decay is of the pulse. What is that steepness? And we we know in mathematics that the voltage that you would impose from the tip of the lightning rod into the soil is an aspect of the impedance and the dIdt. So if there's a high impedance, you have a high dIdt, you're going to get a really high voltage. And there's a lot in the standards, and there's a lot of evidence, there's a lot of information in testing labs that we're talking about what would look like millions of volts. Testing labs here in the USA can produce up to 2 million volt open circuit strike energies, which is again back to the electric field and how it's going to behave. So that steepness is an incredibly important aspect of lightning. And then the overall energy. For the purposes of science, we normalize it, so that's why you see this over R. But it's basically the current over time, so I squared over time. And you see this a lot in things like fuses, I squared T, and different measures that we use throughout other industries, but it's still a mathematical derived value that we can work from. So in the lightning protection standards, the international standard IEC is very detail oriented for this. We can see that those mathematical values are used to describe lightning. This is derived from the IEC 62305 tables, and it's very common throughout other standards. This data is also very common through the Seeger papers and numerous other academic research that shows what these values can be. And what's nice about using these values is that you can go back and forth mathematically through them, and you can derive or estimate other properties, and you can set your surge generators to produce these waveform values in a meaningful way then you can use that to equivalent between different research areas. So if somebody in the USA has a generator that's capable of producing this set of values, that data can be reproduced for the purpose of showing approximate equivalent lightning parameters. And what's nice about this is that it shows the severity levels, increasing or decreasing severity levels depending on how safe you think you want to be. And this is used to compare the lightning risk for something like a hospital filled with babies and oxygen tanks versus the risk of a metal structure that stores farm equipment. And you can see that you'll still want to protect your farm equipment, but it's not likely to be a huge cause of death, that your risk is so much higher. So what's nice about the IEC methods is that if you have more risk, you can apply more principles, and it will tell you, the standard guides you in how to set up the methods to protect more vigilance, more diligence in the protection of your system. So if we know the amount of current that you think you're going to have in your lightning pulse, you can then estimate the rolling sphere radius. And that's been achieved through numerous studies, but again, it's based on an exponential of the peak amount of current that is measured in the pulse. So if you think you're going to need to withstand very modest lightning, it's a very low current. And a low current means it's a smaller radius. And the risk, remember, we're talking about controlling the risk. If your risk is, so to speak, average, we consider that a 10 Ka pulse, and that's a 45 meter rolling sphere. And you see the equivalence through other standards, like NFPA uses 150 foot, approximate 45 foot meter rolling sphere radius to do their calculations. And the standards are fairly well aligned for that, what we would say is the normal, industrial risk category. The IEC methods allow you to pick a smaller radius to be more diligent if you think you have a higher risk evaluation. So that's really what that rolling sphere, it's back to that math of what does that lightning step leader look like, and how worried are you that it's going to get into the nooks and crannies around your structure and get in and touch something that you don't want it to direct strike onto. So if this were something, a building down here that's full of gasoline, you really don't want that to be a source of ignition. You would apply more lightning rods to prevent it from striking that can of gasoline. That's what that allows you to do, some flexibility and some intelligence into how you select your protection methods. There are many protection methods. You can use the rolling sphere radius and roll that over. That's really great for things that are maybe complex structures. Then there's methods that are not complex structures. Maybe the protection angle is easier. If you're consider down here in Florida, for instance, we have power transformer stations that have masts, a single mast over the area. And that allows you to estimate what's the protection below that mast. And it's very effective for what would be considered a very simple structure area. Or maybe you have a very simple structure that you can apply a mesh onto. And so what this lets you do is a table like this out of IEC, and this is also similar in NFPA, other standards. It lets you select a method that makes sense for your structure for the simplification. You don't need to spend all day doing a rolling sphere around something that looks like a simple mast. You can, but these methods are available and they're consistent. You'll get a very consistent result. So if you apply a table like this and you say my average risk class 3 is that I can predict a rolling sphere angle if my height is 40 meters. So if I know my tower around my structure is 40 meters, like remember that photograph of that TV antenna getting struck next to the sycamore tree might have been, let's say, a 40-meter tower. That's 120 feet. That's pretty tall. But let's just pick a number. 40 meters tells me that my angle needs to be about 27 degrees. So that's an angle of declination around that area. And by the way, the house was protected from a direct strike, but it blew out the TV. But you didn't get the direct strike. So at least the science of that is, you can look at a picture and confirm that that's not a bad, reasonable expectation. So the pillars of lightning protection, we like to call them the fundamental pillars. If you take any of these out, the building's going to fall down because you don't really treat this as a menu of options. You don't get to pick one and then not apply the other. So that's what's really nice about them is they make sense when you look at each one and then compare it to the others. You can start seeing why they are dependent on each other. The air termination system is what you want at the top of your building. The down conductor system brings that lightning current to the earth termination system, all while you pay attention to separation distances between structures that you don't want to talk to the lightning, and bonding for structures that you cannot prevent from talking to the lightning. And we'll take a look at what does that actually mean. That you cannot prevent it from striking something that's just like your metal foundation of the building. So you bond. But if you don't want it to talk to the antenna, you separate. And that's really what that means. And when you look at examples of this, you'll really see it in things like damage at a structure. And here you can see what looks like side flash from the original strike. This isn't necessarily the original lightning energy. This is probably a portion of it. But you can see even that was enough to burn out and cause significant fire damage in a structure. And this is why all the factors are important. You can't leave one out and expect not to have problems. So let's look at each one. The air terminal system for a building. And this is a reasonable sketch of the topic. And what's important here is the placement of the terminals are designed to give you, in this case, a rolling sphere solution. So you can strategically pick where to put the terminals and what to use as a lightning conductor. For instance, here at the edge of the building, it's reasonable to use the parapet side, the metal flashing maybe of a building is very common. And then that has to be bonded. So here you have an air terminal, lightning down conductor connections, and equipotential bonding. But notice over here, you have what can be an air terminal mast in the center of the structure, and it's preventing attachment onto these victim structures like the air chillers, the handlers, your solar arrays, your photovoltaic array. And it's separating the lightning from that structure and still acting as an air terminal. So the concept is simultaneous sort of solutions. You have to do all five, but you can't just start bonding everything together, or you are inviting trouble into your air chiller. And we've seen that with customers that had used air terminals on something like that looks like an air chiller like this. I guess they obeyed the standard, but what they didn't obey was separation. So now that structure that you want to protect is now part of the lightning path. Now, keep in mind, when we talk more about equipotential bonding, all the metal things that are up here are doing something like this solar array has electrical ground. That's not lightning bond, but it's an electrical ground. And the motor that goes into this chiller, this air handler has a green wire, and that's electrically bonding for fault safety of the motor. But you still don't want to attach that doesn't mean put a lightning rod on it. Just because it has a green wire doesn't mean you want your lightning rod on it. So sometimes you separate from that electrical bond. That's what separation gives you. So even just talking about the first aspect, you see that you have to pay attention to all the aspects. Now we'll talk about the down conductor system, and right away you see the points. Separation to other electrical systems that you want to keep away from your lightning path. And so selecting your down conductor is a great idea and having it run the side of the building, but you can see a couple of mistakes. This might be a metal flange. If that's a metal flange and it's within flashover distance, the NFPA code calls that bonding distance, and the IEC standards call that separation distance. I use separation line. It's essentially the same thing. That separation will flash to that. So you should bond it. That's what the standards would say. Either separate enough to not, or bond it in order to make that a safe system. So again, just talking about one aspect of the 5 pillars, you're already looking at 2 or 3 others that you have to pay attention to. The earth termination system really isn't that much different. You still have to pay attention to all the other aspects of the electrical system. What's nice about the IEC methods, again, here I'm showing that you have options for what you can realistically do at a site. Picture this, maybe this building is surrounded by concrete, and you're going to be very challenged to get a lightning rod an earthing rod in the first place, let alone build a ring. So there are things you can do with your lightning earthing system. So this terminology type A and type B is used to describe what would look like a single earth electrode versus things that are rings or foundation earth electrode systems. Lots of methods to do this that are safe, effective ways to disperse lightning into your earth. It's also really important to remember that your earth termination system at the ground level, the lightning earthing rods are to be connected to the other earthing rods that are within their influence, and the water pipes and things like that of the system. They should be connected if they're next to them, if they're within the influence of the soil. And there's a big discussion about what's that distance. So you see things like 5 meters, you see other numbers that come up. Motorola has a standard, and it dictates something that looks like twice the depth of this rod is the distance between rods. So that's the influence discussion. Again, these are this one topic can go for a long time. I'd like to separation distance. Now this one is a little bit more, I want to say it's definitely better in the IEC methods than what you see in the NFPA methods. I'll put it right out there like that. But again, subject to discussion. But what separation distance allows you to do is to calculate how far apart you should be from the other bits of metal to avoid flash. So if there's a wire, which is metal, or a roof beam, or something that you really care about, like an antenna or a radio or a security camera, anything that uses wire and metal, you need to be separate from at least a distance, a separation distance that you calculate to avoid the risk of side flash. And remember, the IEC methods give you higher current ratings, which would impose more separation. So that's one of the reasons that the IEC methods are somewhat better than NFPA, is because we can be more diligent and expect a higher lightning current. We can also expect that we need more separation. So there's a lot of discussion points about this, even a slide like this where you can talk about what's bonded, what's not bonded, what's separated. But separation distance is one of your pillars. If you disregard it, you will have poor results. And then a lightning equipotential bonding. So this is, again, one of our pillars. You can see things that you want to bond to your lightning system. If it goes past the flange at the roof, if it goes past a metal structure that's probably going to get hit anyway, like this vent stack is probably not that important in this application. It might just be a hot air vent stack. But if that were natural gas burn-off stack, that's a different conversation. You don't want to put an ignition source. Lots of discussion. But here's the point. You have a lightning rod. You have an air terminal. You have a down conductor system, but it's going past an electrical box, and it's too close. You haven't kept it far enough away, because that electrical box has some purpose, right? It's up there for a reason. It's not just somebody didn't put that box there because it was the best place, to store their radio. They put it there because they have to have it on the roof, this controller box. It's got a ground wire in it doing its electrical safety thing, but now you've got the high risk of flashing into it. So lightning equipotential bonding, maybe you should have moved that farther away. And then when you're going past this vent stack, okay, it's all right that you bond to it because it's dead metal that isn't doing anything else. So that's the purpose of lightning equipotential bonding, is to either electrically bond it or keep it separate. There's other reasons for bonding, of course. So you've got to have bonded metal for grounding, for electrical safety, and you have to have bonded metal for static control, but don't bond it to your lightning unless you really want to. And that's the point. Pay attention to it. Don't disregard it. So you see something that looks like that when you're looking at a lightning equipotential bonding and the earth termination system. And all of this metal being bonded together. You want to bond your rebars, you want to bond that stuff together because that creates a very safe equipotential bonded system. It reduces things like touch step voltage that will occur if you've got lightning in the structure. You could have high touch step voltage around that pillar, for instance. So again, a great deal to talk about in this topic. But just remember, bond that stuff. But what about electrical wires? You can't bond electrical wire. You can't short them to earth to safely protect. So you use surge protection devices. And what that SPD does is it provides bonding, equipotential bonding, for what cannot actually be electrically bonded. You're controlling the voltage momentarily during a lightning event. Otherwise, it's actually acting as sort of like your separation distance. It's your electrical separation distance. So you're controlling it only when it needs to be controlled with lightning or surge damage. And that goes for all of your AC power lines as well as your data lines throughout a system. So this is just a nice little sketch of something that looks like an isolated air terminal and separate earth reference. In this case, we've taken an example where the customer wants to obey the principles, the 5 pillars, but they're doing it in a very clever way for them. Is they're allowing the lightning to attach to an isolated air terminal that uses isolated methods to bring that current 4 meters away from the side of the structure, which keeps it well away from the other ground rod of the structure. So specifically what this customer wants is a fall of protection angle calculation for a class 1, the most rigorous lightning protection category that's recognized by IEC, so that lightning is the lowest risk that lightning will discharge directly into this structure. That was his goal. And what this gives him is an isolated air terminal, an isolated down conductor, and an isolated earthing electrode from his radio. So theoretically, during a direct lightning strike event, this radio sees a modest electromagnetic effect and maybe some ground potential rise at this distance, upwards of 6 meters away. That's calculated to be a modest ground potential rise that would cause the least disruption to his operation in even the most severe event. And that's what paying attention to the 5 pillars, if you click the box and say, yes, I paid attention to each one, now my system is maximum protection. You see other examples of this in other high value asset type applications where maybe NASA doesn't want the hydrazine to be struck by lightning while it's on the launch pad. And so here you have isolated air terminals from the larger launch pad structure. And if you could zoom in enough, you would see that these large masts, these tall masts have a ground strap, but it isn't necessarily connected in one big giant mesh. This ground mast is probably separate from the earth over here, just based on the architecture and distances involved. And they don't need to be bonded together. So don't bond it unless you have to, in this case, because you want to keep that earthing system separate from the rest of your structure while that victim, that very high value asset full of explosives is on a launch pad in Florida with the highest lightning density in North America, or close to it. So even a slide like this, you can walk through all the aspects of lightning protection, the pillars of protection, and point to what this set of designers spent a lot of money and time to install for a very critical application. So during our discussion, you'll see that I've talked about a lot of different topics related to lightning protection. There's incredible depth and breadth and level of detail material available. Any one of these standards is useful for confirming, what you're doing in your own scope of practice. The IEC NFPA 780 methods are certainly fairly well harmonized for what's considered the LPL3 level of lightning protection. The other standards you'll see globally, British standards. There's massive global, not massive, but very widespread global adoption of the IEC 62305 methods. MIL standards you'll see applied. They're very consistent with the definitions of lightning and the different stroke levels. You'll see fairly good alignment between standards. And again, with my suggestion that IEC offers the user more diligence, We also see that the IEC methods align a little bit better, I'd say a lot bit better with mill standards. You'll also see Seeger and Senelec and International Lightning Meteorological and Detection Conference, the ILM and ILDC. These conferences, numerous publications and really great science on lightning effects. Very respected authors and experts, Ray Conovan Martin, on the lightning effects literature that they've got in print. I reference that one because it uses that sycamore tree. And then, of course, always pay attention to local variations and jurisdictions with authority. There's certain areas of the world where they may or may not allow certain methods of lightning protection to be applied. So that's always important to be to consider. So Dane talked a little bit about us. I don't want to linger too long on our materials. So I wanted to give the audience, our attendees, a chance to ask some questions about what we've covered today. I'll open the microphone if anybody does wish to add some comments.
Yes, Mark. So there were a couple of questions submitted while you were presenting. I can just go through the list of questions and we can address them. The first question here, Mark, is what is the minimum voltage to be expected for a lightning strike?
The minimum voltage. Well, it's based on lightning charge building up in the air and then provoking an electric field strong enough to punch through the dielectric withstand of air. And when lightning is measured, we're able to measure things like the electric field strength, which is usually, when you're measuring, it's up in the kilovolt, hundreds of kilovolts. So if you're on the ground measuring like a lightning storm coming in, and there's lots of services that have these things that are literally looking for the electric field, it's in the hundreds of hundreds of kilovolts because it's at a distance. If you for instance, when they've done testing at Camp Blanding and they've launched rockets, Dr. Martin's team does a lot of this work. They actually have measured what looks like weak lightning because the rocket provoked a premature attachment point that wouldn't otherwise have attached. So the charge was building up in the cloud. They raised their little antenna up and said, hey, here comes a couple of 100 kilovolts. Let's shoot a rocket up into it. If it was enough to provoke lightning, it would have made lightning. But when the rocket pulls that copper wire up to it, it gives it an attachment point and it provokes the lightning at a lower level. So it's baby lightning. Not that there's any such thing as baby lightning. It would be insulted to be called baby lightning, but it's not as big as a Wrath of God strike that has to travel 20 miles through air.
Yes.
Great question, but it's
the second question we have here is the size of a grounding grid or the size of a grounding rod. Does that depend on the strike energy level, and thus does it also depend on the swirl resistivity?
That's a great question for our next session, but the answer is yes, it actually does depend on the strike severity. If you're designing a system to the IEC most rigorous class 1, it will guide you that the depth of that earthing rod needs to be more if you're worried about higher risk levels for the same soil resistivity.
And I see
that's a great question.
I see there's a follow-up question here as well, where Mohammed asked, is the earth electrode type B, as it is in IEC, a mesh of multiple vertical rods connected together, or is it physically just a ring conductor installed close or around the structure?
I think we'd have to look at that one offline and make sure that we answer that one. Stephen, you've also done a lot of work on the earthing rod.
Yes, Mohammed, what I can say is, the type 2 earth electrode that IEC describes in 6305 only consists of a grounding ring that is installed around the structure. You can include earth rods to increase the conductor that you need to have in contact with the soil, but as it is an IEC as a type B, it does not include earth rods. Earth rods are considered a type A grounding system, but then if we do the calculation to determine the amount of length of conductor we have to have in contact with the soil, you can increase that by adding earth rods as well. So we have a question here, Mark, where Mohammed also asks, as you mentioned, that every structure in an area of expected lightning strikes puts out a step leader. ESE technology says the same thing, but they put out a faster step leader to attract that downward stream. So how are they not any good? This is an answer that he gets when he has to do with EAC technology.
Rakov and Martin, in fact, have a paper that discusses that topic, and they're able to show that the testing that we're able to do in the lab is conclusive that it is not provoking a faster step leader. It's as same or as equal as a step leader. And they found no evidence that it is, in fact, early or faster. So I think the burden of proof is on the proving it exists and not proving it doesn't exist. But so far, the experts could not prove it exists.
Yeah, I see we have a number of questions where people asked about the arguments against ESC, and I can also mention that we do have an ESE a white paper on our website where we address conventional lightning protection systems and comparison to ESC technology. That also lists quite a lot of arguments that you can go and find on our website as well. Then we have a question here. How can I determine the class of LPAs? That is asked by Ali.
Oh, that's a great question about the IEC methods. It starts with risk evaluation. Next week, when we go into standards a little bit more detail, we'll actually talk in depth about the risk evaluation methods available through NFPA, through IEC. They're very similar evaluations, but in the IEC methods, it allows for more diligent effort. And I think that's where you get your option to select the more diligent methods, the more stringent class, based on your risk and based on what you know about your customer, your facility.
Yes,
great leading question.
That also addresses the question you had, Bara. We asked what is needed to decide on the LPL level. Then we have a question here asking about the difference between IEC standards and the NFPA. So we can build up an entire webinar just on that topic. So thanks, Carlos. I think we'll take that as a topic for one of our webinars that we'll have in the future.
And we have another article on our website about that topic. There's updates forthcoming on both standards that paper will be readdressed. But as of now, what's in effect and what's adopted, it's a reasonable discussion of the key differences. Yeah, thank you.
Yes, then we also have a few questions about separation distance. Michael asked the question, he said, what is the minimum separation from another metal object where you don't have to bond? So I think, Michael, you're asking, how can I correlate the separation distance to determine how can I correlate the separation distance to my requirement to either bond or not bond? So I don't know if you want to say something about that, Mark.
Well, it's back to the risk evaluation. The risk evaluation guides you to select the minimum protection factor from the list of options 1, 2, 3, 4. So if your risk is really high, a hospital full of babies and oxygen tanks, then your protection methods are suggested to be more stringent to reduce your risk to an acceptable threshold. And if you've done that, it tells you what category, what class of protection. Then you apply that to the calculation, and then your heights and your distances all factor in. So it becomes, by factoring in your risk, it becomes a factor in your future calculations. I think that gets you most of the way to the answer.
Yes. We are receiving more questions that we actually have time for. We have
Okay,
actually
that's
already
actually great.
exceeded our 5-minute limit. So I'm just going to take 1 or 2 more questions, and I think we will reply to each of your questions on a separate email, and perhaps in our next webinar, which will be an hour longer, 50 minutes longer, it'll be an hour. We'll make the Q&A session a bit longer so that we can address more of these questions. This webinar is also recorded. That's one question here. Mark, we have a question. The guy he asked that if you could choose, what is the most effective earthing electrode configuration, a type A or type B? And I'm asking you that question because there's a few questions here about that. Can you also comment on the touch and step potential performance between a type A and type B system, grounding system?
Terrific questions, and those are actually really lengthy answers, dependent on your customer's applications, of course. So somebody like a power plant is going to want what looks like a big grid and rings and then strategic vertical earth rods, and somebody that looks like a residential building might have a very simple ring and 1 or 2 rods. At my house in Spokane, Washington, I had 1 earth rod. It looked almost like a single rod, but all of my services were linked together, so I had everything bonded. Touch step in a system like that is going to be really high because you've got everything concentrated in 1 rod, so your voltage gradients are really high in the soil, or in whatever your conditions are. So then treatment of things like concrete layers and things become really important. But that's a great topic for when we move on into our upcoming sessions, because we're going to spend a lot of time on different methods.
That's a comment that I also wanted to make. We will be in depth, going each one of these different topics in our upcoming webinars. And if you are not able to join us for our we are recording it and we will make it available for you to download. Yes, thanks, Mark. I think it was a very informative presentation, and thank you everybody for joining us today. We will send you guys the registration links for the upcoming, and we hope to see you again. Thank you.
All right, thanks everybody. Have a great day. Be safe.